Good afternoon again, and this is the last video for chapter 31, and later I will post the ones for 32. Here we have an LRC series circuit. The source is operated at its resonant angular frequency. At this frequency, the reactance XC of the capacitor is 200 ohms, and the voltage amplitude across the capacitor is 600 volt. The circuit has R equals 300. What is the voltage amplitude of the source? Now, what is needed, of course, here is that at resonance, the impedance of the circuit is going to be equal R. And we can, of course, use the information for the capacitor to calculate what is really the current of the circuit. V is going to be divided by X. I is going to be V, the potential difference amplitude divided by XC to calculate the current. I will be able to calculate then the voltage amplitude for the resistor. The resistor is 300 and the current through it is 3, then it's going to be 900. At resonance, Z equals R, but XC is not 0. All right. Now the next one. In an LRC series circuit, L is 0.280 Henry and C is 4 microfarads. The voltage amplitude of the source is 120. What is the resonance angular frequency of the circuit? Okay, maybe this one should be like before that one. What the source when the source operates at the resonance angular frequency, the current amplitude in the circuit is 1.70 amperes. What is the resistance R of the resistor at the resonance angular frequency? What are the peak voltages across the inductor and capacitor and the resistor? We know that at resonance, again, Z is going to be equals R, and, XL and XC, they are equal. They're going to cancel each other, and they're going to keep on the impedance, the resistor. Remember, Z is the square root of R squared plus XL minus XC all squared, and then when they are equal, they're going to cancel. We know also to calculate the resonance frequency omega 0, it is 1 over square root of LC. V, the potential difference amplitude for the resistor for the circuit is going to be I times Z. For the resistor, I times R. For the inductor, it is IXL, and okay, just one second. This is why I don't like to use the, to zoom in, zoom in out, because, all right, let me see here, 16. Yes, I did solve this one, this one, this one, this one, this one. Okay, we know VC also VL is IXL, and we know that VC equals VL. Now, what is the resonant angular frequency of the circuit? It is 1 over square root of LC, and from that you will be able to calculate, okay, that it is 4945 radians per second. At resonance, we know that, VR equals V, because VL minus VC is going to be 0. And then we know that the current I is 1.70 amperes at resonance. So R is going to be equal to Z, and it is V divided by I. And then it is 120 divided by 1.7, and that is going to be 70.6. At resonance, VR equals 120 volts. VL, VC equal I omega L, because remember they are equal. Then we can use the equation for the inductor, which is I omega L 1.7 times the omega 945 radians per second times 0.280 Henry, and that is 450 volts. Okay, now a parallel plate capacitor having square plates 4.5 centimeter on each side. Okay, then apparently this is to calculate the area. And 8 millimeters part is placed in series with the following. Okay, then for the capacitor, we know that we can calculate capacitance from epsilon 0 A over D, and apparently these information were provided for this purpose. An AC source of angular frequency 650 radians per second and voltage amplitude of 22.5. This is the information for the source. A 75 ohm resistor. Okay, then this is my R, and an ideal solenoid that is 9 centimeter long, has a circular cross section 0.5 centimeter in diameter, and carries 125 coils per centimeter. Apparently, this is also to calculate what is really the L for the solenoid, what is the resonance angular frequency of the circuit. Okay. I added here a notice that use 30.15. This is to show you about like how to calculate the L for a solenoid. Okay, the inductance of a long solenoid is L mu 0 A n squared divided by L, and the inductor has n turns that they are really 125 per centimeter. Then I need to multiply by its length, which is 9 centimeters, to get the total number of coils. Also, we know that this resonance frequency, it is F0 1 over 2 pi square root of LC. This is not omega, this is the frequency, not the angular frequency. Epsilon 0 is 8.85 10 to the negative 12. This is the electric constant. Mu 0, it is 4 pi 10 to the negative 7. These are my constants. I can first calculate the capacitance as epsilon 0 A divided by D. Remember, this is square plates. Each is 4.5 centimeter. We need to convert into meters here. A square, this is the area. And then this is the electric constant divided by the distance between the two plates, which is D. And it is converted here into meters. And this is the capacitance, 2.24 10 to the negative 12 farads. L, it is the inductance, and it is mu 0 A n squared divided by L, and I have calculated L here. Now, omega 0 will be 1 over square root of LC, and then this is really the angular frequency at resonance. Next. Now here I have a solenoid that has 2900 closely wound turns, cross-sectional area, 0.45 square centimeters, mean radius 9 centimeters, and resistance that is R equal 2.8 ohms. Here, okay, and ignore the variation of the magnetic field across the cross-section of the solenoid. What is the amplitude of the current in the solenoid if it is connected to an AC source that has voltage amplitude 24 volts and a frequency of 495 hertz? again here, this is what I need. I need first to calculate L for here. Here I think I like the sentence is not complete. Like, of course, it is connected to this resistor. Here L, it is mu 0 n squared A divided by 2 pi R. And then XL, it is 2 pi FL. Z, it is here, we don't have a capacitor. It is the square root of R squared plus XL squared, and I equals V over Z. Then here I did use this formula to calculate L. I did calculate XL here using this equation. I found Z as square root of R squared plus XL squared. Remember, these are not added like resistors. These are phasors. And then I is going to be V divided by Z. This is the amplitude of the current, which is 6.26 amperes. This one also is similar, but similar, I mean, to all the ideas that I have presented so far, but it's like showing you a circuit where you're gonna, look at the reading of different voltmeters. Here I have, I will say, the 3 voltmeters. The first one, V1, V2, V3, they are reading the voltage across R, L, and C. And there is like V4 is going to be, measuring between L and C, and V5 is going to be the overall. And then I will say, let's start with 5 infinite impedance voltmeters. This is to tell you that they are really ideal voltmeters. They have very high resistance, so that they will be able to measure, the voltage. Calibrated to read RMS values, are connected as shown in the figure. Let R equal 200 ohms, L for Henry, 0.4 henries, and C, it is 6 microfarads, and V is 30 volts. What is the reading of each voltmeter if omega is 200 radians per second? And we're going to repeat when omega is 1000 radians per second to show how really the impedance is going to be affected by the behavior of the capacitor and the inductor at low and higher frequencies. First, I'm gonna solve here for the 200 radians. I listed my values. I calculated ZL. It is omega times L. It's 80 for the capacitor. The reactance is, or the impedance, I call it sometimes, like my term is not correct. This is the capacitive, we call it reactance. Okay, the impedance is for the circuit. Okay, 1 over omega C, and this is 833. And I know the value of the resistor, then I am able here to calculate what is really Z. Okay, and it is Z equals 779. I can calculate the IRMS value, okay, based on my calculation for VRMS divided by Z. I have the voltage amplitude is 30. Therefore, I will be able to calculate VRMS as V divided by the square root of 2. And from that, I got the VRMS as 21.2 volts. I have calculated IRMS to be VRMS here divided by Z, 21.2 divided by the whole impedance, and this is going to give me the current, okay, which is 0.0272 amperes. V1 reading is going to be the voltage across the resistor, therefore it's just IRMS times R, and that is 5.44 volts. I can, for V2 reading, the second voltmeter, VLMS is going to be IRMS times XL, and this is 2.18 volts. And finally, VC is the reading for the third voltmeter, and it is just the IRMS multiplied by the capacitive inductance, by capacitive reactance, sorry. Okay, and then here V4 is going to give me the between VL and VC, and therefore is going to be VL minus VC over square root of 2, and that is the reading 20.5. For V5 reads VRMS is 21.2, and it should be showing like the total VRMS that we have calculated already. Now I have repeated here. Of course, I need to redo the impedance thing again for the 1000 radians per second. I did calculate also what's going to be the new current, and then I recalculated the values, and then I will say the first one is the reading for the first voltmeter, the second voltmeter, the third voltmeter, and then this is the fourth, and finally V5. We know that the frequency, resonance frequency, it's omega 0, 1 over square root of LC. And then one of the frequencies that was given, it is below resonance, and one is above resonance. And when the frequency is below the resonant frequency, we're going to find that XC is going to be greater than XL, because now it's going to be dominant. And when it is 1000 radians per second is greater than the resonance frequency, XL is going to be greater than XC. Now, during the lecture, I was talking a little bit about filters, or like maybe I did say we're gonna have something in the problem solving. Here I have a high pass filter, which is, as an engineer, you will be able to, work with these. One application of LRC circuits is to have high pass or low pass filters, which filter out either the low or high frequency components of a signal. A high pass filter here is shown in the figure, where the output voltage is taken across the LR combination, and the LR combination represents an inductive coil that also has resistance due to the large length of the wire. Derive an expression for V out over Vs, the ratio of the output to the source voltage amplitudes, as a function of the angular frequency omega of the source. Show that when omega is small, this ratio is proportional to V and thus is small, and show that the ratio approaches unity in the limit of large frequencies. Now here the voltages across the resistor and the inductor are 90 out of phase, and therefore we know that V out is going to be, using Pythagorean, V r squared plus VL squared. XL is given as omega L, and XC it is 1 over omega C. Then I can solve for Z using this equation, and from that I will be able to calculate what is really I, and V out will be I times the impedance of that is the circuit excluding the capacitor, and therefore we will be able to find the expression here, which is, I'm going to substitute the value here of Vs here, the value of I, which is this one here, and also the value for Z. I combine this one and this one here, and then I will be able to say V out over Vs this is going to be the ratio. When omega is small, okay, as omega is smaller, okay, we are going to say that this is going to be r squared plus omega, like this here. The denominator will go to 1 over omega squared over c squared. And then r squared plus omega squared L squared will go to r squared. And therefore, we're going to have omega RC as omega becoming small. Now, when we're going to have omega large, as we get larger, or r squared plus omega L, which is the numerator, is going to go to omega squared L squared, and we will find also that the numerator is going to go to omega squared over omega squared L squared, and then like they're going to cancel, and then as omega becoming very large, V out over V source is going to be just 1. Here, the LRC parallel circuit. Okay, all the circuits that we did before, they were a series circuit, and this one is when it is parallel. And then here we have a resistor, an inductor, and a capacitor that they are really connected in parallel to an AC source with voltage amplitude V and angular frequency omega. Let the source voltage given by V at an instant equals V cosine omega t. We're going to show that each of the instantaneous voltages, they're going to be equal to V at any time. This is the parallel circuit, and the current is going to be equal to all the currents, where I is the current through the source, and then IR, IL, and IC are the currents through the resistor, inductor, and capacitor, respectively. What are the phases of IR, IL, and IC with respect to V? And we're going to use the current phasors to represent these. In a phasor diagram, show the phases of these 4 currents with respect to V, and use the phasor diagram of part B to show that the current amplitude I for the current I through the source, it is given by this expression. Finally, show that the result of part C can be written as V divided by Z prime, and with 1 over Z prime is this value. Now, for the circuit, which is a parallel circuit like this one, see here, all of them connected parallel to with the source. At any time, the same rules apply to parallel DC circuit as to the AC circuit as the DC circuit. Voltages are the same and currents add up. Now, for the resistor, we know that the current and the voltage, they're going to be in phase. For an inductor, the voltage leads the current by 90, and for a capacitor, the voltage lags with a 90. Now, we know that they have equal potential drops over the capacitor, inductor, and resistor. Therefore, all of them are equal. For the currents, they're going to add up. I can calculate IR. It's very easy to calculate it. V over R is always in phase with the voltage. And I can find IL, which is V over omega L. This is the inductor reactance, which is lagging the voltage by 90. Now I'm talking about the current. IC is V omega C, which leads the voltage by 90. And we are gonna have the phasor diagram here. It is drawn here. This is the current amplitude. This is across the resistor. This is its voltage. Now, if you look at, again, the rules, remember, IC and IL, they have 90 degrees between them. Then their resultant is going to be IC minus IL. And therefore, when I want to add, this is IR plus IC minus IL. I can use the Pythagorean. Then I squared equals IR squared plus IC minus IL squared. This is V over R, and this is V omega C, and this is V over omega L squared. And this is verification for part C. From part C, we know that I equals, this is like I squared. I did not take the square root. I equals V square root of 1 over R squared omega C minus 1 over omega L squared. I is V over Z, and then 1 over Z, we can calculate it that. And for large omega Z, going to 1 over omega C, and the current in the capacitor branch, it's much larger than the current in the other branches. I hope this was clear. Thank you very much for listening, and see you soon. Thank you.